Well, hi there, boys and girls. Today we're going to talk about how to find derivatives of inverse functions. And so we're going to try and remember some things from pre-cal. A famous set of inverse functions are natural log of x, which we have learned about, and e to the x, which we have talked about, and we're going to learn a whole bunch more about that. So the exponential function e to the x and the logarithmic function natural log of x, they are inverse functions of each other. Geometrically, this means that they are reflections across the line y equals x. And if you plug one function into the other, you're supposed to get x out. And so that's supposed to be the answer. They're supposed to basically cancel each other. And the inverse is denoted f inverse, f to the negative 1. This does not mean 1 over f. It's the inverse function. We've got some properties here. Let's go through a couple of things that we need to know. Not every function has an inverse. It has to pass the horizontal line test, or has to be 1-to-1 in order to possess an inverse. If it does have an inverse, there's only one, though. That inverse is unique. Let's go through some pre-cal stuff. Finding the inverse function of f. First thing you want to do is you want to rewrite it as y equals the square root of x minus 1. If it's in function notation, go ahead and replace f of x with y. Step 1, switch x and y. So we'll write this as x equals square root of y minus 1. Step 2, solve this for y equals. So I'm going to have to square both sides, and then I'm going to have to add 1 to both sides. So I will get that x squared plus 1 is equal to y. Now we have to be careful. We've created a quadratic, but this quadratic and the domain and range is what we have to be careful about. So let's get to that. Graph f and f inverse on the same set of coordinate axis. I'm going to come back to that. I'm going to do the domain and range first. The relationship between these graphs is that they are, not reciprocals, they are reflections across the line y equals x. Let's talk about domain and range first of all. For f of x, what's the domain? What numbers can we plug into the square root of x minus 1? Well, we can't do the square root of a negative number, so we're going to have to guarantee that x is greater than or equal to 1. Now, the range for f is going to be all y values that match it, and all those y values are going to be greater than or equal to 0. Now, for the inverse function, you have to flippy-floppy the domain and range. So our inverse function's domain is going to be x is greater than or equal to 0, and the range is going to be y is greater than or equal to 1. So let's graph these things and show you what I mean when you have to be careful. The square root of x minus 1 is a square root function shifted right 1, and it looks something like that. Now, x squared plus 1 in its pure form is a quadratic both left and right, but we have to be careful with our domain. Our domain is only x is greater than or equal to 0 because it came from the range of f. The inverse's domain will come from the range of f, and so we only want to graph the right-hand side of the parabola. We don't graph anything over here because this graph didn't exist down here at all. And of course, here's the relationship between those two. They're reflections across the line y equals x. All right, so let's go ahead and do some calculus with this. I've got two functions that are inverses of each other, x cubed and cube root of x. Let's go through and discover something that's pretty neat. F of 2 would be 2 cubed, which is 8. F prime of x would be 3x squared. So f prime at 2 would be 12. Now, f inverse at 8 would be the cube root of 8, which is 2. Now, this is sort of neat. F of 2 is 8. F inverse of 8 is 2. Well, that should make sense because the domain becomes the range, and the range becomes the domain for inverse functions. They go through flippy-floppy points. What we're going to do now is discover the relationship between the derivatives at these flippy-floppy points. The derivative of f inverse, so let's find out what that derivative is. That would be 1/3 x to the negative 2/3, which would be 1 over 3x to the 2/3. That's called f inverse prime. Now, f inverse prime at 8 would be 1 over again, remember this is power over root when you have a fractional exponent. So I'm going to do the cube root of 8 first, which is 2. 2 squared is 4. 4 times 3 is 12. What do you notice about these numbers? Well, they're reciprocals of each other. So the way I like to say it is that inverse functions have reciprocal slopes at flippy-floppy points. the slopes are reciprocal. So let's go through some examples of this. The derivative of an inverse function. This is a messy little relationship, but that's exactly what is true. This formula is true, and I'm not going to go through and read this to you. I'm just going to show you how to use it. Sometimes you're given all the pieces of information that you need, and we can just put it into the formula. I'm going to go ahead and organize this, though I always like to write down f and f inverse and show the flippy-floppy points. This just helps me. F, we know, travels through the point 3, 5. Therefore, f inverse would travel through what point? That's right, 5, 3. So f inverse prime of 5 is going to equal, this is what I'm using the left-hand side here, 1 over f prime, not at 5, but at 3. The slope here for the f inverse at 5 is going to be the reciprocal of the slope of f at 3. And we are given that piece of information that that's 7/2, and of course 1 over 7/2 is equal to 2 over 7. This is going to take some practice, but a lot of things in calculus do. Now sometimes we're not given the pieces of information that we need, and we've got to go through and solve and find it. We want to find f inverse prime at 2. And I'm going to say, again with organization, I want to write an ordered pair for f and ordered pair for f, and I want to write an ordered pair for f inverse. Now we want to find f inverse prime at the x value of 2. That means that the y value for f is 2. Domain for f inverse is the range for f. What we don't have is this missing piece, this missing connection. The y value for f inverse would be the x value for f. So sometimes you are going to actually have to set f equal to its y value in order to find this x coordinate. And by looking at this, the only number that would make this true is 1. 1 plus 2 is 3 minus 1 is 2. So my missing piece of information is 1. So I can use my formula that f inverse prime at 2, the slope of f inverse at 2 is going to be 1 over the slope of f at 1. See how these are the x and the y of the flippy-floppy point, the way I'd like to call it. So I just need to find f prime, plug in 1, and then go ahead and make it a reciprocal, put 1 over that. So f prime of x is 3x squared plus 2. So f prime at 1 would be 5. So my answer for f inverse prime at 2 is 1 over 5. All right, let's do that again. A lot of practice. I've got g and g inverse. I really like to organize this with the fact that g goes through an ordered pair and g inverse also goes through an ordered pair, and their relationship is that the x and y are flippy-floppy. We want g inverse prime at 2, which means that g is going to travel through the y value of 2. What we don't have is this missing point. The missing point, we need the x value for g that will make the y value 2. We need to set g of x equal to 2. And the only thing you can take the square root of and get 2 would be 4. So x plus 1 would have to equal 4. So x is equal to 3. So that's my missing piece of information. So g inverse prime at 2 is going to equal 1 over g prime. Where? Right here at 3. The slope for g inverse at 2 is the reciprocal for the slope of g at 3. So I need to find g prime of x, which is going to equal 1 over 2 square roots of x plus 1. You can verify that, but we've done that so many times it's probably worth memorizing. So g prime at 3 is 1 over the square root of 4 is 2. 2 times 2 is 4. So when we put a 1/4 down here, and if we flip that over, we get the answer of 4. All right, let's just do this one more time. I want to find f inverse prime at square root of 3 over 2, so I'm going to have an ordered pair for f and an ordered pair for f inverse. This really helps me organize this because there's so many pieces to this. We want f inverse prime at the square root of 3 over 2. That means that the y value for f is the square root of 3 over 2. That's the square root of 3 there. That's a 3. All right, so I need to find out what x value makes cosine x equal to the square root of 3 over 2 on the interval from 0 to pi. what angle will make cosine square root of 3 over 2 on that interval? And that answer is obviously pi over 6. Pi over 6. Why is that true? Cosine is adjacent over hypotenuse. If you do the Pythagorean theorem, then the opposite side would be a 1. That's a 30-degree angle, which is pi over 6. So we found our missing piece of information, so we can set up our formula. F inverse prime at the square root of 3 over 2 would be 1 over f prime, where? At pi over 6. The slope of f inverse at square root of 3 over 2 is the reciprocal of the slope of f at pi over 6. So we need to find f prime of x. F prime of x is going to equal the derivative of cosine of x, which is negative sine of x. So f prime at pi over 6 is negative 1/2. We already have the angle here. The sine of pi over 6 is 1/2, and we just have to put the negative on it. So we're going to put a negative 1/2 in the bottom down here, and then we flip that over and we get an answer of negative 2. So I know that's a lot of pieces of information, but with practice you can make this second nature, and I will see you guys tomorrow.